Okay, next intro says the next concert on the tour is the benefit concert, and all proceeds go towards the Make-A-Wish Foundation. They're hoping to raise enough money to send 3 children to Disney World, and because of this, they're selling all of the tickets in groups of 3. The Two Turtles in a Sloth website states that 3 tickets will be $135 and 6 tickets will cost $270. The group is trying to figure out how much each of them will have to pay. So here's the question: what is the price of one ticket? Well, a lot of students might want to go ahead and say, well, I know it's 135 and divided by 3, but there might be some kind of hidden processing fee. So let's make sure that that is correct. Let's look at the cost of that 270 and make sure the difference between 270 and 135 is the same. So we're going to see the difference in the amount of money. 270 minus 135 is $135. So there isn't any processing fee. So we looked at the difference of the money. We looked at the difference of the tickets. So 6 minus 3 is 3. Okay, so that tells us now that we can compare that. If it's $135 for 3 tickets, we're going to divide those out. 135 divided by 3 is $45 per ticket. So again, what we looked at is we looked at the difference between the amount of money spent and the amount of tickets, and then we compared those by creating a ratio and then actually evaluating that ratio and figuring out it's $45 per 1 ticket. If you remember that unit rate, that's what it is. We just created a unit rate. Next one, they're selling special t-shirts for this concert. The following table states the prices. So again, what's that price for 1 t-shirt? What is just that 1 unit rate? Again, let's go ahead and double check. Let's look at the difference between the prices. So 126 minus 63, it looks like it's going to be $63 for how many t-shirts? Well, 6 minus 3, $63 for 3 shirts. Okay, so how much is it for just 1? Let's go ahead and create a ratio and compare. 63 to 3 shirts means that each shirt is $21. So again, the steps that we did, we looked at the difference between the prices, the difference of the shirts, and then we compared them together. So we looked at it verbally, like number 1. We looked at it in a table, like number 2. Now we're going to look at it in a graph. It says the band has the following graph up by their t-shirt stand. It shows the total amount of t-shirts they need to sell in order to reach their goal. So question 3, how many t-shirts do they need to sell per hour in order to get these kids to Disney World? Well, let's go ahead and look at the dots that they have in there. We're going to visually see what's going on. We're dealing with hours and t-shirts. So it looks like between the hours of 1 and 4, they're going to have to sell between 60 and that 240. So how many t-shirts is that? 240 minus 60 is 180. So they need to sell 180 t-shirts in 3 hours. So 180 shirts in 3 hours. We're going to compare that. 180 divided by 3 is a grand total of 60 shirts per hour. So what we just did on all 3 of those is we looked for what's called a rate of change. We looked at how the rates changed over time. And again, in math, remember that changing means that we are dealing with subtraction. So we are going to be using subtraction a lot here, right? Since we're dealing with rates, rates are always comparing 2 different things. We're looking at dollar amounts versus tickets, dollar amounts versus shirts. We are looking at t-shirts versus hours. So the different vocab that we're going to be looking at and comparing them in many different ways. So we should be ready to go ahead and get out the notes and vocab for this section. Okay, objective is to determine the slope of a line from a graph, equation, or a table, which we actually just did in that introduction. And we talked about the rate of change. It's a ratio that describes, on average, how much one quantity changes with respect to a change in another quantity. We're going to look at the algebra side of it now. It says if x is the independent variable and y as the dependent variable, then the rate of change is looked at like this: the change of y over the change of x. Okay, we didn't look at it like that in the introduction, but technically that's what we did, because look at how we could have written that information as a point. 3 tickets cost 135. 6 tickets cost 270. So what we did was we looked at the change of our dependent variable. The cost of the tickets depends on how many tickets we buy. So we took 270 minus 135. And we compared that to the change in x, our independent variable. We compared it to the 6 minus 3, and we ended up with our 45. So we did do a rate of change. We did look at it with x's and y's. We just looked at it in a real world situation. So change in y, the dependent, over change in x, the independent. So let's go ahead and try that. We're going to use the table to find the rate of change, and then we do have to explain its meaning. So let's compare what we're talking about. We're dealing with the total cost versus the number of computer games. So again, we're going to look at how much does it cost per one computer game. Well, change in y again. We're going to figure out the difference in the cost versus the difference of how many computer games that we did. So again, change. Change means that we're subtracting 156 minus 78. That's going to tell us the difference in cost versus the 4 minus 2, difference of how many games. So 156 minus 78, it looks like, again, no hidden costs, so it costs us $78 for 2 games. So how much is that just for one game? 39. So looking at that, again, we're finding the rate of change. Rate of change is 39. What does that mean? It means it's $39 per game. I ran out of room over here, so I don't want to make this sloppy, but this does equal 39. Okay, so again, rate of change, looking at the change of our y versus the change of our x. Looking at it in that real world context of understanding what we just found out. Go ahead and try guided practice 1. Okay, finding that rate of change, we're looking at the change of our y's, 96 minus 48, minus the change of our x's, 6 minus 3. That question arises again, do I have to look at that 9 and 144? No, we're assuming that the rate of change is constant all the way through, so we don't have to look at them. But 48 over 3 is 16. So rate of change is 16, but now we have to explain what that means. Well, we have the area of the surface versus the floor tile. So that means that we have 16 inches squared for one floor tile. Okay, so explaining that in layman's terms, 16 inches of floor surface is covered with each of the floor tiles. All right, rate of change, just always remember that it's y over x. And again, speaking of that constant, that that rate of change is constant all the way through. It says, so far you have seen rates of change that are constant. Many real-world situations involve rates of change that are not constant. So let's look at this example. It says the graph shows the number of people who visited the U.S. theme parks in recent years. So we're supposed to find the rates of change for 2000 to 2002, so this one right here, and then from 2002 to 2004, so those next couple of years right here. Okay, so let's go ahead and do that. 2000 to 2004. Again, let's look at our rate of change. We ended with 324. We started with 317. So we had 324 million. We're looking at the change there. And then we're figuring out how many years was that. Well, it looks like 2 years. So I'm just going to put 2 right there. Okay. So let's go ahead and do some computation. 324 minus 317. We have 7 over 2, which means that it's about 3.5 million people per year. Okay, there's our rate of change between 2000 and 2002. let's go ahead and look at the other ones. My color coding is backwards. That's going to drive me nuts. So that was that piece. Now we're looking at the next 2 years. Again, let's go ahead and look at that rate of change. 325, we're comparing that to 324 over a 2-year period. So look at this, 1/2. So it looks like here we just increased by 0.5 million people per year. Might have been a pretty slow year. Okay, so rate of change, looking at it in a table, looking at it here, we can actually see it visually with the numbers. Other times we might have to actually look at the graph itself and count up like we did in the introduction. Explaining the meaning of that rate of change, we went a little bit too far. I apologize on that. But it looks like it increased by 3.5 million per year between 2000 and 2002. It increased by 500,000 people per year between 2002 and 2004. How are the different rates of change shown on the graph? Okay. Good question, because it gets us to start thinking visually. Looking at the line between 2000 and 2002, that's steeper. Looking between 2002 and 2004, it's definitely more narrow. So the steeper the graph, the greater the rate of change. So that's what we're going to say. We're going to say the greater rate of change is steeper. Okay, so again, starting to look at the difference between algebraic numbers versus a graph, and how we can quickly look at that graph and realize which is going to be the highest numbers. Okay, if they asked us between which 2 years did we have the best amount, well, we could quickly look at that. 2000 to 2006 is definitely the steepest spot. All right, go ahead and try 2000. Go ahead and try guided practice 2. Okay, again, asking you to visually analyze that graph. Without calculating, find that 2-year period that has the least rate of change. We can look at it and see that between 2002 and 2004, it's the narrowest part of the graph. Because of that, we know it's the least amount of change. So didn't really have to do any math on there. We could just visually see that. Okay, a rate of change is constant for a function when the rate of change is the same between any pair of points. So all of the problems so far, they told us that we know that they were constant. Now we have to see, we know that linear functions also have that constant rate of change. That's why we can draw a line between it, because it's always constantly stair-stepping the same amount all the way through. So now the question is, we have to determine whether these functions are linear, making sure that between each one of these, we do have a constant rate of change. So what we have to do is we're going to have to compare a couple different numbers until we can either say yes or we're going to say no. Okay, so this is what it's going to look like. We're going to have to look at the difference between those. We have -8 minus a -6. We're looking at the change between them. Make sure we have 2 negatives in there, over 4 minus 1. We have to see if that's the same as -10 minus the -8 over 7 minus 4. We have to see if that's the same between -12 minus 10 over 10 minus 7, and so on. Okay, we're going to get our nice calculator out and let it pretty much do the work on this. Again, since we're doing some division, we're going to have to put that parenthesis in there. Here's our negative button down here. This is different than the subtraction sign. So when I say this in my head, I'm going to make sure that I'm hitting the right buttons. -8, I am subtracting a -6. I want to divide that by 4 minus 1 I know is 3. So that gives me, again, math fraction, that gives me a negative 2/3. So this first section is negative 2/3, and there's my test. Everything else has to equal negative 2/3. So I'm going to go ahead and keep going. Negative 10, I'm subtracting a negative 8. I'm dividing that one by 3. Okay, that one passes. My calculator disappears, so I'm going to keep going with these. A negative 10 divided by 3. It passes. Last one. Divided by 3. Looks like we got it. Okay, so each one of those does come out to be negative 2/3. So, is this linear? We're going to have to say, yes, yes it is. Okay, explain. Yes. Constant rate of change of negative 2/3. Okay, so again, we're going to do the same thing on this. I'm not going to create this big ugly mess over here. I'm just going to go ahead and write what I get for those answers over here. And I might not have to do all of them, but let's see. Okay, again, getting used to this. I know that I'm taking the change of y. So the 12 minus the 10, and I'm dividing that by that negative 1 minus the negative 3. Okay, rate of change of just 1. So there's our test. We're going to do 16 minus 12. Again, you could quickly do that in your brain and understand what that is. We're going to divide that by a 1 minus a negative 1. 2. So can I stop right away? Yes. Is this linear? No. And we are going to say there is not a constant rate of change. Okay, so how do you test for a constant rate of change? You go through and make sure that that rate is the same between every single one of those values. And now it's your turn to try. Okay, 3A came very close, but we had that one little oddball that made it a no. All right, looking at 3B, we did have a constant rate of change of negative 5/3. Okay, most of that I didn't do in the calculator. I could just kind of quickly do it in my brain. So I showed you how to use the calculator. Don't get too hooked on it unless you absolutely need it. Okay, we dealt with rate of change. Now we're going to change that up a little bit and talk about slope. The slope of a non-vertical line is the ratio of the change in y coordinates, the rise, to the change in the x coordinates, the run, as you move from one point to another. It can be used to describe a rate of change. So, rate of change and slope, again, synonymous. Slope describes how steep a line is. The greater the absolute value of the slope, the steeper the line. The graph shows a line that passes through the points negative 1, 3, right here, and 2, negative 2. So this is going to show you a couple different ways that you can get this answer. Again, we know that it's the change in y. So we call it the rise over the run. Okay, how far did we get? How far did it take us to get from one point to the other? Okay, so here it looks like we rose 1, 2, 3, 4, 5, and we ran 1, 2, 3. Notice that this is the slope of a negative line. I always tell kids, think about your skateboard. If I put my skateboard on the left here, what am I doing? I'm going downhill. So this has a negative slope. If I put my skateboard down here to the left, what am I doing? I'm going uphill. So this is a positive slope. Okay, so left to right, what is happening to your skateboard? We can quickly see this should be a negative slope. We could quickly see that this one is going to be a positive slope. So we have already done this. We've done the change in y, the change of x. Now we're going to look at it specifically as a graph, looking at it as the y coordinates. If they just gave us 2 points, we're going to look at it as taking that second y value. And again, I'm going to go back to my 3 and 135 and my 6 and 270. And this is exactly what we did. We looked at y2, which means the second y value, which was 270. We subtracted y1. So this is how anytime that I have to find the slope of something, I automatically put arrows in. I'm going to take my 270, subtract 135. Then I'm going to take my 6 and subtract my 3. And I put that arrow below because this is going to be my numerator. This is going to be my denominator. Okay, and I'm always going from the second, notice the second point, to the first point. I'm comparing the second x value to the first x value. That's what those little 2's and the 1's mean. This is y sub 2, the second y value. Okay, y sub 1, the first y value. So hopefully that helps us out a little bit. Okay, so that's what we're going to do down here. We're actually going to look at it 2 different ways. We're going to find the slope using numbers, then we're going to graph it, and we're going to look at the rise and run between those slopes. So very first thing, I see slope. That means that I'm going to put an arrow between my y's, then I'm going to put an arrow between my x's. So that means that I'm going to take 5 minus 0, and I'm going to divide that by 1 minus a negative 2. So 5 minus 0 is 5. 1 minus a negative 2 is actually 3. So according to my math, the slope of this is 5/3. Let's go ahead and plot this. Negative 2, 0, and 1, 1, 2, 3, 4, 5. Okay. On this, I tell the students to start from that left one, and I'm going to figure out how far I rose and how far I ran, because again, it's rise over run. I went up 1, 2, 3, 4, 5. I went over 1, 2, 3 between those 2 points. So did I get a slope of 5/3? Yes. And again, how far do I know when to stop? Always make a little right triangle between those 2 points and then count how far did I rise over run. Slope of this guy, 5/3. Okay, looking at this one, again, very first thing that I'm going to do, I'm going to draw arrows between my y's on top. I'm going to draw arrows between my x's on bottom, always going from the second to the first. So I have negative 3 over minus 4 to negative 3. We're subtracting, remember, because this is change. Change in math is always subtraction. So I have a negative 7 over a positive 5. Is that the truth? Let's look. Negative 3, 4, and 2, negative 3. First thing that I notice here is that this is a negative slope. My skateboard is going downhill. So always start with that left dot. How am I going to get over there? This time I actually have to drop. So instead of climbing, I had to drop 7, 1, 2, 3, 4, 5, 6, 7, and I had to run 5. So because I dropped, there's where the negative comes into play. I climb a wall, it's positive. I drop, it's negative. And I went over 5. So my rise is a negative 7. My run is 5. Over here, my rise was 5. My run was 3. So 2 different ways that we can look at this. Visually, in that graph, and then mathematically. All right? One more of these guys. So right away, slope. Here we go. Those arrows really do help us stay focused on what we are subtracting from each other. So negative 1 minus a negative 1 over 2 minus a negative 3. This is kind of weird because look at this. Negative 1 minus negative 1 is a 0 over a positive 5. Well, what's 0 divided by 5? It's actually 0. Can we have a 0 slope? Well, let's go ahead and graph this and see what happens. We have -3, -1, and we have 2, -1. Look at this. We've got a horizontal line. So we do have a slope of 0. Okay. I always say if I put my skateboard on this slope, I would have 0 fun because I'm not going anywhere. So slope of 0 for a horizontal line. We're going to talk about that in just a minute here. But slope of 0. How far did I rise here? I rose nowhere. I did run 5, and that's where that 5 comes into play. But slope of 0. All right. I didn't give you graphs here, but go ahead and use that slope formula to find the slope of these 3 lines. Okay, one thing that we didn't see with that example, since they were all fractions, was that if I do get a 2/1, go ahead and simplify that down to the whole number or the integer. So 4a should have been 2. 4b was another 0 slope, horizontal slope, and then 4c we can simplify down to -1/2. Okay, so we've talked about a horizontal slope. We understand that, again, 0 fun there. Now we're going to talk about an undefined slope. So let's go ahead and find the slope between these 2 points right here. Again, drawing in arrows. I know that I have -3 minus 4 over -2 minus -2. So adding the opposite, we have a -7 over, now we have a huge problem because we have a 0. This is definitely different than what we had before because 0 divided by something is always 0. We cannot have a 0 in the denominator. So this is where we call this undefined. Okay, so let's go ahead and look at what this looks like. We have -2, 4, and then we have -2, -3. So vertical. Okay. Again, going back to my skateboard, I definitely do not want to put my skateboard right there because I'm going to have a couple broken bones. So undefined slope right here. We cannot divide by a 0. Guided practice, you could only imagine what you're going to get as an answer for this. But let's go ahead and go through this. 7 minus 3 over 6 minus 6, which again, we cannot divide by a 0. So this is called an undefined slope. You can't say that it's a 0 slope. 0 slope deals with horizontal. Undefined slope deals with a vertical line. Okay, I'm going to show you a couple tips and tricks on that down here. Because again, there's 4 different types of slopes we can get. Positive and negative are pretty darn easy. Slope of 0 is our horizontal line. Here's a trick. Notice what happened up here. Our y values are the same. So slope of 0, y value is the same. That way you don't have to go through all that mess. Undefined slope, x values, the same. Okay, so kind of a nice little tip to realize what type of slope we are dealing with. Okay, very last one. Remember our little slope formula because now again they're missing one of the pieces and they actually give us the slope. So this is kind of like our percentage change problem if you remember that. As long as we have our formula, we can plug in what we know to find out what we don't know. So I know that y2 minus y1 equals x2 minus x1, or over x2 minus x1 is going to equal my slope. And I believe that they used m up here, and I hope they did. Somewhere, sorry. Yes, they did, because m is what you're going to see for slope. Ym, no idea. Maybe they liked marshmallows. But slope is m. I'm going to go ahead and plug in what I know. Okay. I'm also going to use my arrows because I really like my arrows. Helps me a little bit more because I know that I have r minus 4 over -5 minus 1. And I know that that change should give me 1/3. Well, guess what? I pretty much just created a nice little equation that I can solve. So I'm going to go ahead and keep simplifying. Negative 5 minus 1 is negative 6. So I'm going to say that r minus 4 over negative 6 equals 1/3. And I'm going to keep going because this looks a little bit easier. I'm trying to get r by itself because, again, I'm trying to find that value of r. So these two lines will have, or these 2 points will have a slope of 1/3. So I'm going to go ahead and multiply by a negative 6 on both sides in order to get rid of my denominator, which I did. I got r minus 4, and that's going to equal a negative 2. Negative 6 divided by 3 is negative 2. Final step. I'm going to add that 4 over. So I know that if I put a 2 in for that y value and I found the slope of this, I would get a slope of 1/3. Okay, use the formula, plug in what you know to solve for what you don't. Go ahead and give that a shot for guided practice 6. Okay, this one's a little bit different because the variable we were looking for is in the denominator. So again, I still figured out what it was I needed to know. Negative 4 minus 6 over r minus a negative 2 equals my slope of negative 5. I simplified that down to negative 10 over r plus 2 is negative 5. Okay, I had to get rid of an r plus 2 as a denominator, which is really weird. So again, I multiplied both sides by an r plus 2, which gave me negative 10 equals a negative 5 times r plus 2. So in this step right here, I really should have distributed that negative 5 through, but I looked at this and I said, hey, negative 10 is nicely divisible by negative 5. So instead of doing that, I'm going to just get rid of the negative 5 and divide it over here, which you can do. Again, if you do something to one side, you can do it to the other. So I simplified that down to a 2, and I was just left with an r plus 2. Subtract that guy over, r equals 0. Okay, I kind of did the same concept over here. Again, the value that we're looking for was in the denominator. So I had to multiply by a 5 minus r on both sides. Okay, instead of distributing that negative 8 through, I went ahead and divided it over. Not quite so pretty because it was a fraction, but I realized that probably means my answer is going to be a fraction anyway. So negative 2 divided by negative 8 is 1/4. I don't know why my pen is not working. There we go. Okay. So 1/4 equals the 5 minus the r. I subtracted the 5 over. 1/4 minus 5 is a negative 4 3/4, but there was still a negative attached to that r. So again, I have to change the signs of each side in order to get r completely by itself. So they both become positive. I will tell you this is a pretty high level type of problem. So as long as you understand the slope formula, understand why it's the change of y over the change of x, you should be okay. I think this is about as high as you're going to get with a story or with a high-end problem like that. Okay, otherwise you should be set to start the assignment for this section.